Still in, you'd have to kill me.
Okay, direct your attention up front.
Wrong.
Hello.
Hey. Hi.
I did a lab about temperature, and it's actually two different labs. And we were really confused about what we were going to do with a temperature probe, because a lot of the labs we did already involved that. So we tried the first one. The first one we thought of was dropping water from a bucket into another bucket of water below it and seeing the temperature change. And then we did some calculations and we figured out that you probably need 4,000 meters into the sky and then drop that down and then it'll change only 1 degree. But we still persisted through that and we used the temperature probe and dropped it from like about 1.87 meters. And the water changed. There should be a graph, but probably not. The graph looked like it went up just a little bit, like 0.01 degrees Celsius. And then we repeated that 4 or 5 times, and then it just randomly goes down, and sometimes it goes up, and then sometimes it goes down. So that was basically error, and there's not really anything that we could take from the data. So we kind of threw that lab away, but we wrote a purpose of it, and that's part 2. See if water dropped from a certain height will change potential energy into heat. But we changed our lab into the relationship between the resistance of a material on the heat output of a battery. And we used a 9-volt battery because we found that that releases a lot of heat when you put a piece of metal between the two, like the plus and minus things of the 9-volt. So the equipment, thermometer, and we used the voltmeter and ammeter, but they weren't the Lager prototypes, like the old school ones. So we had different types of coins made from different materials, and because the resistance of the coin itself changes the amount of heat that is released by the battery. And then the rest of this part is basically the lab that we failed to do because we can't go into space or wherever. For the procedure of part 1, the battery lab, we take a fully charged 9-volt battery, and then we close the circuit of the 9-volt battery with a coin. And the first coin we used was a Canadian penny, and it was made of 98% copper, and that has a really low resistance compared to other metals. And then the second time we used, I think, a quarter. No, it was a USSR commemorative nickel quarter something dollar. And that had a really high resistance compared to copper. So we took data, we let the coin sit on the battery, and then we put the temperature probe on the battery, and then we recorded the temperature change of the battery over 1,000 seconds, which is like 16 or 17 minutes, I think. And we did this 3 times with a fully charged 9-volt. So the first time it starts with 9 volts, and we let it cool down to room temperature, which is around 23 or 4, and then it rose really fast for the first 200 seconds, and then it stayed there, and then it kind of fluctuated, and that was because of the immense amount of error that we had in this lab. And then after 1,000 seconds, we recorded the voltage of the battery again, and it turned out to be 8.2. Then we did the same experiment with the coin, same exact coin, except this time it has 8.2. And this time it took about 600 seconds to reach to its plateau temperature, and then it stayed there until 1,000 seconds. And the third time we took it, it was about 7.5 volts, and you can see each time it dropped around a volt, or 0.8 or something volts. So then the third time it only went up 4 degrees, 5 degrees, and it immediately plateaued around 200, 300, 400 seconds. Let's just say 300. And that showed that the 9-volt did not release as much heat as it did before. This time we took a nickel coin, the second time around, took a new 9-volt battery, and it almost is the same thing, but this time using a nickel coin, it took almost 600 seconds to reach its maximum temperature, while the first time it took like 200 seconds. And that is because of the resistance of the nickel coin.
Can you call attention to the maximum temperatures reached by the two different coins also? Comparing fresh
The copper
batteries, I think
coin,
that's interesting.
Got to 35 degrees Celsius. And the nickel coin on the first try got to 38 degrees, 37 degrees Celsius.
But took much longer to do it.
Yeah, it took a lot longer. Then we took it, did the same experiment, except with 8.1 volts. And sadly, almost, it just died, kind of. Basically, there's barely any temperature change. I think there was only like 1 degree, and then it just fluctuated up and down, 0 to 1 degree change. And we did it one last time just to make sure we didn't mess up, and it's about the same thing. Where this last time is 7.4 volts, and there's barely any change at all, and it was not even noticeable. And the change in voltage is almost the same exact thing for both coins, but the nickel took a lot more energy. And then this one was the water, the dropping of the water from 1 meter-ish. And if you look at the scale on this, it's actually, this much distance is only 0.04 degrees Celsius. So we thought that it went up 0.04 degrees Celsius. And then we took it again, and then it was like, hey, look, we have something to work with. And then the third time we took it, just went down. And then after that, it went down again. And then it was just a waste. For sources of error, when you're messing with temperature, we figured out that temperature has a lot of error when you don't have like the perfect surroundings to work with. A lot of heat is released into the environment. I think we would have done a lot better if we put the battery or the water in like a really, really, really insulated material and then put the temperature probe in there. We couldn't find any 9 volts in Drun's house, so we took like we didn't have any new packs of 9 volts. So we just had a lot of scattered new 9 volts that had their little rubber caps on them. And so the 9 volts were different brands of battery. The material was the same, I think, but the brands could probably cause some type of fluctuation in the data. Heat sucks because it runs away. We did this over a course of 2 or 3 days, so the temperature of the room that we did it in changed in the 2 or 3 days, so that's kind of weird. Well, actually, that's normal. The hot air, we noticed that the temperature, when we did the water pouring lab, we noticed that the temperature of the water, when you hold it up at a higher altitude, was a little bit hotter than the temperature at the bottom of the floor. On the floor. So that kind of sucked. We couldn't, for the mathematical analysis, we were looking all over the internet for like some type of equation that we could find, and then we just put stuff together, and Jordan did most of the calculations, and the paper is lost somewhere in space. Well, in conclusion, we figured that the 9-volt battery was basically a really strong power source, but it runs out of power really fast, because over the period of 30-45 minutes, the battery basically drained itself out to around 7.4 volts, and at that voltage, it's almost useless for a lot of things that the 9-volt is used for. So don't put coins in your pocket and then put a 9-volt, because that would you lose money. For the second lab, we did the water thing that failed, and we basically used MCAT as energy, and then we tried to make that equal to MGH, and then we found that specific heated water is like 4,185, and then basically means you have to drop it from 4,185. And then we tried to find a different material that was household that we could drop, and there wasn't any that we could find. There was a lot of chemicals that were, I don't know, chemicals. And I think the lab was mostly a failure, but we learned a lot of stuff about temperature and how it sucks. And that's it.
Thank you, Sean. Questions? Questions?
Where'd you get those coins from?
Jordan has a little stash of coins. You know, we were looking through Google to find like the least resistant metal, and it figured that the pennies before like 1980 something were actually made of like 95% copper. But we found that he has a Canadian penny, and those are actually 98 or 99% copper. So we use that instead.
That was just
Thank you, Sean.